Okay, so welcome back. We can start the second part of the activity session with Gino Biondini. Very pleased to have him, of course, and he's going to tell us about middle gas fission from elliptic potentials in potential window. Gino, your research.
Thank you to all the organizers. It's a pleasure to be in Newcastle again. Thank you also to Tamara and Ken, who talked about soliton gases this morning. So introduce some of the things that I will talk about. I will eventually get to soliton gases, but this work is, in a sense, the culmination of various works that I've done in the last few years, and it uses several pieces. So I'm going to try to go slowly and tell you about all the various pieces that are going to come together here. So, okay. There we go. Right now, I think it should work now. Okay, so the first piece, we're going to start by looking at something slightly different, which is focusing NLS. The whole talk is going to be about focusing NLS. And right now, we're going to look at it in the semi-classical scaling. And we're going to take a look at real valued periodic single lobe potentials. So what I mean by single lobe is the standard definition by Klaus and Shaw. There exists a single max and a single minimum within a period. So these are some examples. Okay? These are three big examples. And if you do numerical simulations, this is what you get. So even though these potentials are very different, you get similar behavior. Now, you say here I have 3 and here I have 4. Why? Because the fourth one is actually the well-known sash potential that was studied a lot in the late 90s and early 2000s. So I don't remember, maybe 1/20th or something like that. Okay, so can you try to make sense of what happens here? And of course, there's all the works by Miller and McLaughlin for the sash potential. Can you do anything for the periodic case? Of course, NLS is integrable, so you can look at Zakharov-Shabbat, and Zakharov-Shabbat is non-self-adjoint, so things are complicated. And Tamara and Ken talked about it already this morning. So, okay, so I think that's good. Okay, so this is the Lax pair of NLS in the semi-classical scaling. Z is the eigenvalue, Q is the matrix Q contains the solution of NLS, sigma 3 is the Pauli matrix, and of course this can be written as a eigenvalue problem. This is all well known. Okay. So let's stand closer. So we're going to look at it at this problem with periodic boundary conditions. Of course, there's a long history of spectral theory for NLS for periodic boundary conditions, and in particular, there's a lot about finite genus solutions, but we're not going to use finite genus machine here, just block fluid theory. Okay? So just very basics. You look at the scattering problem, you want to understand the spectrum. So you want to understand the spectrum of this problem when Q is a periodic, spatially periodic matrix. So you look for the block Fouquet normal solutions, rho is the Fouquet multipliers, and the spectrum essentially is the set of values of Z such that rho is on the unit circle. So that solutions are bounded for all real X. Okay? And then we teach it in beginning graduate classes. In order to find the Fouquet multipliers, you need to solve this, in this case, quadratic equation. Delta, the Fouquet discriminant, is the trace of the monogamy matrix, and the monogamy matrix is any matrix that relates, it's the matrix that relates any fundamental solution to itself after a period. Okay? So as I said, the spectrum is the set of values of Z such that rho in matrix is 1, and that means that delta must be real and it must be bounded between -1 and 1. So these gray lines are all the analytic curves. Delta is an entire function of Z. So these are all the analytic curves on which the imaginary part of delta is 0. And then the blue lines, the blue segments are all the bands where the real part of delta is between -1. So you can talk about bands and gaps like in a self-adjoint problem, but bands are not restricted to the real axis and they can intersect at most points. And in particular, the endpoints of the bands are the periodic eigenvalues. These are the values of z such that delta is 1. And the antiperiodic eigenvalues are the values of z such that delta is -1. They correspond to periodic and antiperiodic eigenfunctions. All right. So one thing that you can do is you can compute the spectrum numerically using Fourier-Hill's method. And you see that as epsilon goes to 0, the spectrum localizes the real and imaginary axis. I'm going to give you a bit more detail below in a second, but for now, let's take that as granted. Using that observation, also, if you have a real potential, you can convert the Sakharov-Shabbat problem into Hill's equation with a complex potential. Hill's equation is, of course, the Schrödinger equation with periodic potential. In this case, the potential in Hill's equation is this. Okay? It's a complex valued potential. And so you notice, on the other hand, that the problem becomes formally self-adjoint as epsilon goes to 0. And this was already noted by Zakharov in their seminal work in 1972. Okay? So based on this, for now, we don't have any more justification, but we're going to use WTB just with lambda real. And what's lambda? Lambda is the eigenvalue of Hill's equation, is related to z by the symbol transformation. So looking at lambda real means looking at z along the real or imaginary axis. Of course, I'm going to skip weeks and weeks of calculation, but after you boil it down, you find that the real lambda axis divides into 3 regions. A region where you have no turning points and delta is real and always greater than 1 or less than -1. So that part has no spectrum. That corresponds to the imaginary axis above IQ max and below -IQ max. You have a region where you have, again, no turning points, but delta is between -1 and 1. Okay, this is an abstract star. So that's an infinitely long band. So in the z-plane, that means the real axis plus the segment minus IQ minimum, and then the region where you have 2 turning points where you have bands and gaps, and then you get this asymptotic approximation for the trace of the monadic image, the Fouquet discriminator. Using this, you can now do asymptotics. So you can compute, you can get asymptotic expressions for the number of bands. You can compute asymptotic expressions for the bandwidth, the gap width. You can compute the number of effective solitons. And then what you see is that just like with KDV and defocusing and LS, as epsilon goes to 0, all excitations become effective solitons. However, because all eigenvalues are in the imaginary axis, here all the solitons have 0 velocity, so you get a soliton compensate, which explains, at least intuitively, why you would get that picture. All right, so that's the first part of the story. Second part of the story, let's go a little bit more in detail into the block-Fouquet theory, and can you justify restricting yourself to the real and imaginary axis? So what do we know about delta? We know that it's an entire function of z. We know that the real axis is an infinitely long band. We know the bands can intersect at most once. They cannot form closed curves. And if Q is continuous, you have an asymptotic expression for the Fouquet discriminant as z goes to infinity. This is spurious. All right. So using this, you can get 2 results. You can get bounds for where the spectrum is located. If Q is in L infinity, you can get that the spectrum is confined to the strip in the complex Z plane. And if Q prime is in L infinity, then you also have this bound. The spectrum is confined to this hyperbola. Okay. But now notice you have an epsilon here. So that means that as epsilon goes to 0, the spectrum localizes to this cross. And what I mean is that give me any finite width d. For any width, I can find an epsilon such that the spectrum is inside this gray region. It's contained within a neighborhood of width delta of the cross. All right. So that sort of justifies restricting ourselves to the real and imaginary axis. So that's part two. All right, part three. I guess I have a few more results. So this is relevant for us because in the defocusing case, you have bands and gaps on the real axis, and then finite gap potential is a band for which there's a finite number of gaps. Well, in the focusing case, things are different. You can have bands that intersect the real axis, and any such band is called a spine. And then there's a well-known theorem that says that you take a big enough rectangle, and then outside this rectangle, any band except for the real axis has to be a spine. Okay, so the corollary is that for the focusing case, the number of gaps is always finite. Every potential is finite gap. The meaningful distinction in the focusing case is between finite band versus infinite band potentials. Okay, and in other words, you can call a potential, you can have a potential that's finite band if and only if there exists a big enough rectangle such that, except for the real axis, all the bands are contained in this rectangle. And as a special case, if the periodic and antiperiodic spectrum are contained within, confined to the real or imaginary axis, Q is a finite band potential. And that will turn out to be useful in a second. Let me forget about this. So now let me go to part three. Part three now, we go back to study a special case. And the special case is this. For now, I'm turning off epsilon. I'm setting epsilon equal to 1. And I'm studying this two-parameter class of potentials. Dn is the Jacobi elliptic Dn. These are plots of Dn for various values of m. I'm going to tell you the limiting values in a second. This is a periodic potential with period 2k of m, where k is the complete elliptic integral of the first kind. And without loss of generality, thanks to the phase invariance of NLS, we can take A to be real and positive. So what are the two limiting cases? The two limiting cases are m equals 0 and m equals 1. M is the elliptic parameter. So when m is 0, dm is identically equal to 1. So you have the constant potential. And then the spectrum is trivial to see that it's just the real axis plus the segment minus IA, IA. The opposite limit, m goes to 1. Dn goes to sesh, and so you get this potential, which is potential the case studied first by Satsuma and Yojima in 1974, using the ISE on the infinite line, because in this case the period goes to infinity. And they used a clever transformation from Zakharov-Shabbat to a hypergeometric ODE, and they were able to compute the scattering coefficients explicitly. In particular, this is the off-diagonal scattering coefficient. And you see immediately that if A is an integer, this term is 0, and so you get a reflectionless potential. And in fact, they had a theorem. If and only if A is an integer, this is a reflectionless potential of focusing Zakharov-Shabbat with discrete eigenvalues at these points on the imaginary axis. So these are the two limiting cases that were known. Now the question is, what if M is not 0 or not 1, but an arbitrary value between 0 and 1? And what we were able to prove with Shudan, who's here, Alex, who's also here, and Jeff Orogero, former student now in Kansas, is that if and only if A is an integer, this is a finite band potential. And in particular, if A is integer, Q is a genus 2A minus 1. Okay. So it took us several years to get all the proofs down. So I'm not going to give you the proofs, but I'm just going to give you a little bit of the context. Okay. How does that relate to what we were talking about? It relates because you can set A to be 1 over epsilon, and then you can rescale the problem so that you have a fixed potential, but you have an epsilon in front of you have the semi-classical scaling. Okay, you have to rescale T as well. So again, a little bit of context. Q is real. Dn is a real value function where x is real. So again, we can map Zakharov-Shabbat into Field's equation. This is the same as what we've seen a second ago. And because the N is even, we have a PT symmetric potential. So these results provide also an example of a PT symmetric potential of Field's equation with purely real spectrum. Okay, and also this ODE is a complex deformation of the well-known Lamé equation. What's Lamé equation? Well, the Lamé potential of Field's equation are C times Sn squared. Well, dn squared is 1 minus m Sn squared. So we have again Lamé equation except with the complex deformation. And the theorem of Lamé says that for Field's equation, U is a finite band potential if and only if C is a triangular number times the elliptic parameter. So now what we have is the analog of Lamé potentials for the focusing Zakharov-Shabbat operator. And finally, I'm not going to go through it, but the results also provide an example of a solvable connection problem for Hoe's ODE because you can map this problem into Hoe's ODE as well. So I'm not going to tell you anything about the proof, otherwise that's the rest of the talk. I'm just going to show you a couple of pictures that will become relevant for the last part of the talk. So let me tell you what you're looking at. The horizontal axis is the elliptic parameter m from 0 to 1. And these three plots are three different values of m, 3, 4, and 7. And on the imaginary, the vertical axis is the imaginary axis in the z-plane. And so the red curves are the periodic eigenvalues, the blue curves are the anti-periodic eigenvalues. So you always have one periodic or anti-periodic eigenvalue at the origin for any value of m. And then for m equals 0, that's the constant potential, all the gaps are closed. Okay, so these points coincide. And then as soon as m is different from 0, they open up, the gap opens up, okay, and then the gap grows. And then as n goes to 1, the periodic and anti-periodic eigenvalues collide, and that's because it's a singular limit. The period goes to infinity, and then you get the discrete eigenvalues of Satsuma and Yajima. Okay. All right, so now it's time to put everything together. Okay. So, as I said a second ago, you rescale the potential, you rescale time, and now you go from the problem that we studied a second ago to the semi-classical scaling, but now with a fixed initial condition. So what do we have? We have that if epsilon is 1 over n, the initial condition is a genus 2n minus 1 potential. The spectrum comprises the real axis plus 2n plus 1 symmetric bands along the imaginary axis. These bands are not all equivalent, however. And now we go back to the WKB theory that we did at the beginning. WKB says that these bands shrink exponentially fast, whereas the ones in the gray region, whereas the bands in the white region, in the limit, as according to WKB, they form a continuous band, but now we know that there's also gaps. Okay. So what this means that as epsilon goes to 0, the behavior of the lax spectrum is consistent with the thermodynamic scaling of a soliton gas, or more appropriately, a breather gas, because we have these bands that shrink sub-exponentially. Okay. So, as I said that the bands in the white region, in this case, is the gap that shrink faster. Okay, what's going on here? I don't know. It's not. We tested several slides. I didn't go through the end. Yes, we can this in the PDF. Before you copy it, can you open it and see if the last few pages are okay?
Could you stop sharing the link?
Oh, well, let's go to the end.
Is the news line?
No, keep going. Keep going. There we go. Yeah, that's right.
Can you show again now? Can you show again?
Yeah, sure. I don't know. Maybe the copy didn't go through. That's the only thing that I can get.
Yes. Yeah.
Okay, all right. Okay. So, yeah, I have no problem. Okay, so we're here. Okay. So as I said, we have a breather gas. On the other hand, recent works by Gennady and others showed that even if you have a soliton condensate, which is what you get when you have sub-exponential scaling, because of modulational instability, you get the same result as if you have a set of discrete eigenvalues. So what we really have is a composite soliton gas. What do I mean by a composite soliton gas? You have a soliton gas in which you have a different density of bands in these two regions. Okay, and here they are. You can compute the density of bands analytically. So I give you potential M is fixed. For any given epsilon, you have this curve, this orange curve. I don't know if you can see that distinguishes between the two regions. The regions where you have sub-exponential scaling and exponential scaling. Did I answer your question? Okay. All right. So you get a density of bands. Now, a natural question would be, in what sense do you have a gas? At t equals 0, the nonlinear excitations are all tightly correlated. You have a coherent solution. And that's a valid concern. So what we're going to do is we want to randomize the phases. So Ken and Tamara this morning talked about different ways of producing a gas by randomizing either the discrete eigenvalues or the norming constants. Here we're going to do something slightly different. We're going to add a small amount of noise to the initial condition. Gaussian zero mean identically distributed variables. So to leading order, the Lax spectrum is unchanged. So this is without noise and this is with noise. On the other hand, because of modulational instability, the noise couples to the coherent solution. This is without noise and this is without noise to produce a spatially uniform gas. Okay. And now that you have a spatially uniform solution, you can do statistics and you can compute the kurtosis, which is, like Tamara showed this morning, is the ensemble average of the fourth normalized moment divided by the square of the second. And recent work by Thibault, Gennady, and others, and recent work by Alex and his postdoc Fudong Wang showed that the kurtosis equals this average, or the ratio of these momenta over the distribution of the discrete eigenvalues. F here is the density states, but it's also equal to these moments of the initial condition. That's not important what these constants Cj is. And so what you get is that the kurtosis equals twice kappa naught, where kappa naught is determined completely by the initial condition. And in fact, now that you have this, if you have a single load potential, you can use Jensen's inequality to show that kappa is greater or equal than 2 where kappa equal 2 is reached only if the initial condition is constant. So is this all a dream? Well, you can do numerical simulations of NLS plus noise. So let me tell you what you're looking at. This is time, and this is the fourth normalized moment. So the gray is the envelope of all the noise realizations, and the red is the average. And this is the initial value. As you can see, this is the point more or less where you would have the first gradient catastrophe, and then it settles down. And then now, if you have this is true more or less for any initial condition periodic single lobe that gives rise to a spatially uniform gas. Well, for us, if Q is the end, you can do these integrals analytically, and you get an explicit expression for the kurtosis. And so now what I'm plotting is the kurtosis in blue as a function of M according to according to these two expressions. The red are results from numerical simulations. So this is M equal 0.7, that would be right here. The dashed line is kappa naught. And the stars are the ensemble average of this fourth normalized moment for the initial condition. And so we have a realization now, in summarizing, of a composite soliton gas for which we can compute analytically the kurtosis. Produced by a deterministic initial condition in the semi-classical scaling plus a small amount of noise. So that's the end of the story. And these are the references in case you're interested, and thank you for your attention.
Technical issue. Do you have questions?
Yeah.
I missed at the very end, Ted. You have an analytical calculation of the kurtosis. So
Yes.
computing an expectation value with respect to the random
So what we did here, we leveraged the results by Thibault and Denai. So I didn't do this. Okay, they showed that if you have a fully developed gas, then the kurtosis is given by this expression, and this is also based on the results of Alex and Fudan Long. Okay, so this is not original. If you have a fully developed gas produced by deterministic initial condition, then this is the kurtosis. What we did is sorry?
Bound state.
Yes, bound state. Yes, with all the discrete eigenvalues on the imaginary axis. What we did is say, okay, hey, if you have the M, you can compute these integrals in 2 seconds with mathematical, or you look at burden-free, and then you get this expression. Did I answer your question?
Yeah, so it's just making sure it's not an expectation with respect to the randomness. It's an integral over space.
Well, the result is that this expectation value equals this integral over the density of states, which in turn equals this integral over the initial distribution. That's highly non-trivial. They did the hard part. We just did the easy part.
Just one follow-up. So what's the horizontal axis in this plot?
Here's time. Here's M, the elliptic parameter.
Okay, thanks.
So what you see here is the kurtosis changes, and then it settles down to a value. And then you take this value, this is M equals 7, and you put it here. And then you do the same thing for different values of M.
No.
It was?
Okay, so I'm a little confused. You show that the blue group starts at 2, the kurtosis, right?
Yes.
You said the kurtosis equal only if you the constant.
Well, for M equals 0, the potential is constant. The M goes to 1.
This is the question.
Yeah.
I do not like this more question for Gino or Biondini, maybe that's like what about the formula for the kurtosis? Does it work for any vector state or?
Like it's a bound state. So all the discrete eigenvalues on the imaginary axis.
So they're also formed for general.
Yes, it's slightly more complicated. There's an extra term on the numerator.
Partial.
Only for partial.
No, because this formula is general.
Yes, that's. But, yeah, sure.
Yeah, there's a formula called
Doubling.
There was the, is there any restriction on the density of state that you have to plug in from multiple topologies? You said.
No, this should be valid for any density of states, right?
What was it again?
Should be valid for any density of states, as long as it's along the imaginary axis.
But if there's also support from the real part.
Then thicker, because if you have support of eigenvalues on the real part, you know, outside the imaginary axis, then it's not a bound state solitone gas anymore. Then you have solitons with non-zero velocity, and then things are slightly.
But there is a formula.
Yes, there is formula. Okay, no formula which it's not relevant to this.
I know because I also decided things 2022. Yes, we're gonna chat later.
Well, I think we should change Dino for a right.